Good morning, everybody. So today we are going to go ahead and talk about hypothesis testing for population variance. Back to our structure, P, M, S, proportion, mean, and standard deviation. So we have done hypothesis testing for population proportion. We have done hypothesis testing for population mean. Now we are going to do hypothesis testing for population standard deviation / variance, okay? For mean, we did two scenarios when you know sigma and when you do not know sigma. So we have covered hypothesis testing for proportion, hypothesis testing for mean, and now we are going to talk about hypothesis testing for population variance and / standard deviation, okay? Any question, anybody, before I move on to the next topic? Anything about hypothesis testing for mean, particularly, which was the most recent topic in the last class on Monday? We finished that. Anyone has any question about it that I could address?
Professor, so
Yeah.
I was doing the homework and I got pretty far along. The only part that I got like confused on was where you had to let me pull it up really quick.
Sure.
I think it's like question 5. So I was able to do most of the steps on all 7 problems, except when I would have to show like I can't, let me pull it up. Sorry to take your time.
No problem. Just go ahead and find it.
Do I share my screen or?
No, just go ahead and tell me.
Okay, so it's gonna
problem
be
7, right?
Problem 1, 1, 2, 3. It's going to ask what are the critical regions. So I couldn't find that one. And then I tried doing the test statistic on number 1 as well, and I couldn't do it. I did it on another one, and I followed the same steps, but I didn't get it. I didn't get the answer. So I'm stuck. I'm stuck on test statistics and critical regions.
Okay. So number 1 is a proportion, hypothesis testing for proportion. So let me just...
that would be what we learned last Wednesday, right?
Yeah, last Wednesday, exactly.
Okay, and then so problems 4 through 7 is going to be what we learned on Monday, right?
Right.
Okay. Well, I think I'll just go back to the to your video lectures and then just listen to you again for last Wednesday.
Okay, but let me give you a little bit of background here so that you can work on the problem. So let's say number 1, okay? So the problem number 1 is Roots, a very popular TV show in the 1980s that depicted the lives of African Americans in the US. You want to know whether the majority of the people nowadays have heard about this TV show. You surveyed 350 randomly selected people, and 200 said they have heard of or seen the show. Based on this data, would you reject the null hypothesis that P is equal to 0.5 or 50% at significance level 0.10? So I'll just go ahead and do the problem step by step. This is problem number 1 on the hypothesis testing assignment. So number 1, hypothesis testing. Okay. Roots, let me just write down the problem. Roots. It used to be a TV serial many years ago in the 80s. All right, so first of all, your NP has to be greater than or equal to 10, and your NQ has to be greater than or equal to 10. This ensures normality. Okay, N is the number of data points. So in our case, 350. You surveyed 350 people, and P is 0.5. Obviously, there is 175 that is greater than or equal to 10. So this checks. Similarly, NQ, which is N times 1 minus P, is N is 350 times 1 minus P is 0.5, which is also 175, that is greater than or equal to 10. So both of these conditions are satisfied. What that tells you that it is bell-shaped. Distribution of the sample proportions is bell-shaped. So we needed to know this to be able to apply the central limit theorem or the conclusions of central limit theorem for population proportion. So this is part A. What is the value of NP? You got it, okay? So that's part A of the problem. Part B, what is the value of NQ, which is
175.
175.
And then
Part C,
is 0.5.
what is the null hypothesis? So null hypothesis H naught is P is equal to 0.5. So you don't have to put this, you just put P is equal to 0.5, and that should take it. Let me just check it on my screen.
Yes,
P is
it's
equal
correct.
to 0.5. Yeah, it takes it. What is the alternative hypothesis? Alternative hypothesis is
P is not equal to.
P is not equal to 0.5, which, by the way, on the screen, on the actual answer box, you'd put this way. P, then backslash NE is for not equal, 0.5. And this is what you should type in. P backslash NE, you have to press space, by the way, 0.5. After NE, press space. Okay, let me see if it takes it. P backslash NE 0.5.
Yes, it takes it, Professor, like that. If you do the backslash NE.
Backslash NE 0.5, yeah, it does. Okay, so you don't have to do anything. So that's your alternative hypothesis. Next, what is the test statistic? So test statistic, that's part, so D, so this is part D. Part E, or the fifth part, test statistic, which is Z star is equal to Z sub alpha over 2 times, I even forgot the formula actually, honestly. What is it? The statistic for public. The statistic, okay. The statistic for population proportion is P hat minus P divided by square root of PQ over N. That's the formula. All right. I was confusing myself with confidence interval for a second. So this is what the formula is. P hat, by the way, P hat is X over N. Now, if you look at the problem, your N is 350 because you surveyed 350 people. How many said they have heard of or have seen the show is 200. So these cancel out. 5 goes into this 4 times, 5 goes into this 7 times. So it's 4/7. Okay. So 4 divided by 7 is 0.57. So approximately 0.57. So did you try 0.57 or Alicia, did you get 0.57 as an answer?
I got 1.6. See, I don't know how I got 1.6. Let me see, where did I?
But it's not even take. Yeah, go ahead.
Yeah, no, I didn't get that. The 0.57.
But I just checked it, 0.57, and the system is not even taking 0.57. Why? That's a question I would like to ask. Okay, so that should be the value. So let's check it.
Well, okay, so I did get for p hat, I did get the 0.57, and then so what I did was 0.57 minus 0.5 on top.
Oh,
and
sorry,
then,
I didn't do the calculation. Never mind.
and then
okay, yeah, sorry, never mind. My bad.
no, it's okay. Where I got confused was when I was everything inside the
square root.
Yeah. So I was able to do like 0.57 minus 0.5, which would be the 0.07. And then on the bottom, I put 0.5 times 0.5 divided by 350. And then that's where I kind of got stuck. And then the 0.5 divided by, 0.25 divided by 350 is where I got stuck, and I kind of just got stuck.
Okay. So 0.07 divided by is 2.61. 619. Okay, that's what I got. Yeah, let me try to do the calculation again. 4 divided by 7 minus 0.57, sorry, 0.50 is this divided by 0.026726. 2.67. Okay, so there is a bit of a rounding issue here. Okay, that's a bit interesting. 2.67. So that might be. I took into consideration all the things. I just didn't round it here. That changes the number a little bit. It goes from roughly about 2.62 to 2.67. So try these numbers, okay, and see if it takes it. So let's try.
I entered the 2.67 and it entered it.
2.67, it worked?
Yeah.
Okay.
I'm so confused. I'm still confused on the square root.
Oh, yeah. Okay. So you're still confused on finding this, right?
Mm-hmm.
So first of all, take 0.25 and divide it by 350 on your calculator. Okay?
Okay.
Then take the square root of the whole thing. Whatever answer you get, you take the square root of it. That's going to give you the denominator. And then take the numerator and divide it by the answer. And here is a bit of a sort of technical issue, is that don't try to round it. You might get this answer and it won't take it. It wants you to basically leave the 4/7, okay, minus 0.5. That's gonna be approximately 0.5714.
Okay, I saw the number that you entered now. Once I did the 0.25 divided by 350 and then square rooted it, I saw the 2.67, but it was like 2 zeros. It was 0.0267. 0.0267. So you would just move the decimal over 2 places?
Yeah.
Okay, I got it.
Okay, good. So that's your answer to that one. Then the finding the critical region, remember, you're dealing with a bell-shaped curve and your confidence level is, significance level is 10% or 0.10. You're doing a two-tail test. So this is not equal to, meaning you're doing two-tail test. So that 0.10, which is your alpha significance level, it has to be divided by 2. That's going to give you alpha over 2 is equal to 0.05. So on the right-hand side, the area must be 0.05. And on the left-hand side, the area must be 0.05. And if you do the math, if you look it up on the table, okay, standard normal distribution table, this should be negative 1.645. And this should be 1.645. So your confidence, not confidence, your critical region is going to be this, negative infinity to negative 1.645 union 1.645 to positive infinity. Now, how do you put these numbers? So what you want to do is this. Put a parenthesis, then minus backslash infty. Okay, that's going to give you negative infinity. Okay, and then negative 1.645 close parenthesis. Now, how do you put this union? You put backslash cup, backslash cup. This is a little bit of technicality. This is latex way of saying the union. Okay, backslash cup. That's gonna give you this thing, and then the rest is easy. You do the open parenthesis 1.645 and comma backslash infty. That's gonna give you this infinity, and it should work. And then look at the test statistic 2.67. Does it fall in either of these critical regions? Of course, it's not going to be on the left-hand side, right? It's not going to be on the left-hand side. It's going to be on the right-hand side. So it does fall in the critical region. Therefore, you will reject the null hypothesis that 50% of the people know about the show called roots. Is it okay, Alicia?
Yes, thank you.
You're welcome. Anybody else has any other question? No? Okay. All right. So the rest of the problems should be like this. If you have any question, please let me know. Any other question from any of the assignments, particularly hypothesis testing, that I could answer for you? Okay. So let's move on. We are going to do hypothesis testing for population variance. And we are going to use the chi-square distribution, okay? And chi-square distribution, pretty much the same process. We need to make sure that it's a normal distribution. As it turns out that for this test to work, it is sort of a stringent, stronger requirement that you have a normal distribution. Population you're dealing with is a normal. No, this is a stricter requirement for hypothesis testing involving population variance. So that means your assumption that population that you're dealing with is bell-shaped, it has to be kind of true, all right, for the most part. Now you're gonna do hypothesis testing, null and alternative hypothesis, sigma square is equal to sigma naught some value greater than, less than, not equal to. Okay, your test statistic is chi-square. This is technically chi-square star is n minus 1 times s square divided by sigma square. And that is going to give you the test statistic. And then you will find the critical value, critical regions or critical values from that critical regions. And then you compare the test statistic you found with the critical regions. If it falls in the critical region, you'll reject the null hypothesis. If it doesn't, you won't reject the null hypothesis. And the argument for p-value holds still the same. Even though we don't find the actual p-value, we just show it to you by showing you the area, okay? The area is gonna be smaller. You'll reject the null hypothesis if the p-value or the area associated with the test statistic is smaller. Now, let me move on and do some problems. Okay, here is an example problem, I think, and then there are a couple of other problems. So let's do the example problem first, and then I'm going to do the other two problems. Then we'll go from there. You take a random sample of 10 students at your school and find that on the average, they study 17 hours. So that's your X bar, okay? N is equal to 10 and X bar is equal to 17. They study 17 hours per week with sample standard deviation. So sample standard deviation. So this should be your S is equal to 2.5. Based on this test, based on this, there should be a comma here. Test the claim that population variance is greater than 4. That means sigma square is greater than 4 at 0.05 significance level. All right, so you are testing that sigma square is greater than 4, which is equivalent to saying that sigma is greater than 2. Because if you take the square root of both sides, and we are dealing with positive numbers here, so square root of both sides would yield sigma being greater than 2. Assumption, normal distributed, okay? As I said, you have to make sure that population you're dealing with is bell-shaped. Null hypothesis is that sigma square is equal to 4. Alternative hypothesis is sigma square is greater than 4. Actually, you could put sigma square less than or equal to 4, okay? So sigma square is equal to 4, sigma less than equal to 4, or sigma square is greater than 4. And I think I don't penalize you in the homework system. Technically, if you put sigma square is equal to 4 versus sigma square is less than or equal to 4. What you are trying to gain support for is that the complement of these guys, which is sigma square is greater than 4. In theory, the complement of this is this, not this, okay? So that's what your null and alternative hypothesis, and chi-square star is n minus 1. So the formula is n minus 1 times s square divided by sigma square. So sigma square is 2 square or 4, right? Which is at the bottom. N is the sample size, which is 10 minus 1. That comes from the formula. times S squared. S is 2.5 as we found in the problem. So 2.5 squared. If you simplify all of this, you get about 14.06 chi-square star. Chi-square star or test statistic is 14.06. Now, here is the interesting part I kind of want you to pay attention to. Remember, chi-square distribution is not symmetric. It is stretched to the right, and it doesn't go below 0. So how many tails do you need to consider? Alternative hypothesis is greater than 1, meaning you have to consider the right tail. If it were less than, you'd consider the left tail. So this is the right tail we are going to consider, and my significance level is 0.05. So 0.05 is the shaded region. Associated with that area, 0.05, there is a value. And let me find that value for you. Chi-square distribution, t-distribution, chi-square distribution. Okay, so let's go back and see chi-square distribution. Oh, degrees of freedom is at -1. So 10 minus 1 is equal to 9. So we look at first column in the chi-square distribution table 9, and area to the right of the critical region is 0.05. So if you look at row 9 and area to the right is 0.05 column, it gives you 16.919. So you get this point to be 16.919. So your critical region is going to be everything from this point to the right. So that's exactly what we've got here, 16.919 to infinity. The test statistic 14.06 does not fall in the critical region. So we fail to reject the null hypothesis that sigma square is equal to 4 or sigma square is less than or equal to 4. The test statistic does not fall in the critical region. Why does it not fall in the critical region? Look, 16 is right here and 14 is probably somewhere here. 14.06. 14.06. Now, if you think of the p-value is going to be all the area to the red vertical line, which is obviously bigger than the shaded region by this much, right? So if it's bigger, you do not reject. If p-val is greater than, okay, or equal to alpha is equal to 0.05, then do not reject. H naught or the null hypothesis. In our case, it's sigma square is less than or equal to 4. And that's what the null hypothesis is. And the conclusion, you can base it off of your critical region and test statistic, or you can base it off of your p-value, even though I don't talk about the p-value here. Okay. Any question, anybody, about the problem? Anybody has any question? Okay. Now, I'm going to leave this problem on the screen, and I want you to do the next problem, everybody. Okay? I want you to try it. So I'll give you 5 minutes or so to try this problem. So please work on this problem, look at the steps, because you need to try it. Unless you try it, you won't learn it. Just try to come up with the null and alternative hypothesis, the statistic, and the critical region. And then, of course, you could make the conclusion. So go ahead and try this problem exactly like this one. So take 5 minutes or so, and then we'll go ahead and meet back. Okay, so how did it go, guys? Are you guys, do you guys have any questions, anybody, before I work on the problem? Anyone has any question, anything that you'd like to ask? Okay, so let's continue. So in this problem, you take a random sample of 10 students at your school and find that on the average, they study 17 hours per week with a sample standard deviation of 2.5 hours, exactly the same problem. Now this time, oh, is it the same problem, by the way? Oh, it is the same problem, looks like. You guys should be, nobody told me that. Okay, it's the same problem with 0.05 significance level. Is it 0.05? This time you test sigma greater than 2. It's technically same problem, not. This time you're doing sigma instead of sigma square in the last problem. If you look at the last problem, it's sigma square right here. So which is exact same process, and so you found sigma square greater than 4, right? Which is equivalent to sigma greater than 2. So if you rejected sigma square, which we did, sorry, did we reject? We failed to reject. If you did not reject sigma square, then you won't be rejecting sigma either, because sigma square is greater than 4. Equivalent statement is sigma is greater than 2 if you take the square root of both sides. Since you did not reject, okay, the critical region, we fail to reject, or do not reject sigma square is greater than or equal to 4, right? So we are not going to reject sigma square is greater than 2. Okay, so we are not going to be rejecting the null associated with it, which is sigma is less than or equal to 2. Sorry, it is less than this one, less than or equal to 2. Any question, anybody? Anyone? So you're testing here once again, sigma greater than 2, that's the alternative. All right, so null is going to be sigma less than or equal to 2. So you will not reject the null hypothesis. That's what the conclusion here is. Okay, so let's do the next couple of problems, and then I think we can move to the following section. On average, students at your school spend 20 hours. So that's your X bar. Sorry, 20 hours per week studying on average. Sorry, so that's mu, not X bar. 20 hours per week. You take a random sample of 10 students and find that the sample standard deviation is 3. So that should be your S is equal to 3. And at 0.05 significance level, test the claim that the population standard deviation is less than 2.5. So you need to test that. Once again, the same process. Step 1, normality. We assume there is bell shape. It's a stricter requirement. Number 2, your null hypothesis and your alternative hypothesis. So you're testing sigma is less than 2.5, which is equivalent. Which is equivalent to sigma square is greater than, sorry, less than 6.25. That's what you're doing. Now, sigma less than 2.5, complement of it is sigma greater than or equal to 2.5. That's what the complement is. Now you test statistic, chi-square star is going to be n minus 1 times s square over sigma square. N is number of items in the sample, which is n is equal to 10. So it's going to be 10 minus 1 times s is 3 square divided by sigma is 2.5 or 2.5 square. If you simplify it, 10 minus 1 is 9 and 3 square is 9. 9 times 9 is 81 divided by 2.5 square is 6.25. That gives me 81 divided by 6.25 is 12.96. 12.96. So your chi-square star is 12.96. So please keep that number in mind. Now let me take the screen back. Step number 4, we are going to create the diagram or sort of graph for chi-square distribution, which kind of looks like this. So that's chi-square distribution. Now look, our alternative hypothesis is less than. So we are going to be talking about the left tail. And significance level alpha is 0.05, I think. So this alpha is equal to 0.05. So this point is the shaded region on the left is 0.05. And this point chi-square is equal to, we need to find the value from the table. So let's look at the table. Okay. Let me find the table. So I have my chi-square table. Now, here is the thing you need to remember. To find this point, you have to consider the area to the right, not to the left. Chi-square distribution is cumulative from the right, not from the left. So its area to the right is going to be 1 minus 0.05, which is 0.95. So you'll be looking at the table for chi-square distribution, okay? Your degrees of freedom is going to be n minus 1, which is 10 minus 1 is equal to 9. So that's your degrees of freedom, all right? So you look at area to the right, 0.95, and degrees of freedom is 9, which gives you 3.325. 3.325. So your critical region is going to be from here to here. So 0 to 3.325. And that's your critical region. So that's step number 4. Any question, anybody, about the step number 4, how to find the critical region? Remember, the key thing here is that you look for the area to the right, not area to the left, okay? So 0.05 is the area to the left, which is the shaded region, right? You'll be looking for area to the right. You'll be looking for area to the right. So 1 minus 0.05 is 0.95. So you look for the on the top row of the table, area to the right 0.95, and the degrees of freedom is 9, which is n minus 1, 10 minus 1, and that gives you a value of 3.325. Now, step number 5, does the test statistic fall in the critical region? Obviously, chi-square star is 12.96, does not fall in the critical region. Zero to 3.325. Therefore, we do not reject the null hypothesis. Reject the null hypothesis that sigma, okay, is greater than or equal to 2.5. Okay, so technically we do not reject. This is the equivalent of this is sigma square is greater than or equal to 6.25. So we do not reject sigma square, sigma greater than greater than or equal to 2.5, or equivalently, sigma square is greater than or equal to 6.25. Okay, because if you take the square root of it, you get this. And that's how you will do this problem. Okay, any question, anybody, about this problem? Anything? Alicia, is it okay? Makes sense?
No questions for right now, Professor.
Okay, thank you. Now the next problem is kind of like this. Again, I want you to try it. I have done a couple of problems. So I want you to try it, everybody. So please take a few minutes and work on it, and then I'll come back and work on it. So let's take about 5 minutes or so, okay? Okay, guys, any question on this problem? Anybody? If not, I'll go ahead and do the problem. So in the agricultural city of Salinas, California, you surveyed 13 people, okay? So your N is equal to 13. And find that their average income was 17,000 per year with standard deviation of 3,000. Actually, we don't use this number here. It's just for information purpose. Standard deviation 3,000. At 0.05 significance level, test the claim that the population standard deviation is greater than 3,500. So number one, we assume normality of income. Number two, your null and alternative hypothesis. Null hypothesis and alternative hypothesis. So sigma is greater than 3,500, which is the same as saying sigma square is greater than 3,500 square. Remember, equivalent statement. Complement of this is sigma is less than or equal to 3,500. So that's your null and alternative hypothesis. And then you do the test statistic calculation chi-square star, which is n minus 1 times s square divided by sigma square. N is 13, so 13 minus 1, which is 12, of course. S is 3,000, is going to be 3,000 square divided by sigma square, which is 3,500 square. I could simplify it a little bit. 13 minus 1 is 12, and I could write 3,000 over 3,500 square. These two zeros cancel out. 5 goes into 36 times, 5 goes into 35 7 times. So this in essence becomes 12 times 6 square is 36 over 7 square is 49. So if I simplified it, what do I get? 12 times 36 divided by 49, which is 8.816. So chi-square star is equal to 8.8163, or approximately 8.82. When you are working on these problems, make sure that try the number rounded to 100th place, or sometimes you may want to try 4 digits, depending on the problem, how it wants, okay? So if one doesn't work, try the other one, it should work. So that's your test statistic. And number 4, your critical region. So we are gonna draw it here, the chi-square distribution for you. Remember, chi-square distribution has a stretched tail. You stretch it to the right. Now, do we do a right tail test or left tail test? Look at here is greater than, so you're going to do a right tail. So this area to the right is going to be alpha, which is 0.05 right here. So this is going to be 0.05. Now we are going to have to get the chi-square value here. And the chi-square value, just by looking at the table, degrees of freedom is 13 minus 1 is equal to 12. So if you look at row 12, and this is already area to the right, so we have nothing to worry. We don't need to subtract it from 1. Area to the right is 0.05, 0.05, and degrees of freedom is 12. 0.05 and degrees of freedom 12, that gives you 21.026. So 21.026. So your critical region is going to be from here all the way up to positive infinity, 21.026, all the way up to positive infinity. Step number 5, your test statistic chi-square star is equal to 8.8163, does not fall in critical region 21.026 to infinity. Thus, I do not reject null hypothesis that sigma is less than or equal to 3,500. Why? Look, 8, our test statistic, 8.82, let's say, is probably going to be somewhere here, right? Actually, not even there. 0 is right here, right? So 8 is probably more like here. Okay. 8.82. So now technically your p-value is going to be all this shaded region plus this region, red shaded region, which is bigger than alpha, right? Which is bigger than the blue shaded region. So p-value is greater than or equal to alpha is equal to 0.05. So do not reject the null hypothesis H naught. And that's what should be your answer or conclusion rather. So this is how you do these problems. I kind of did 3 problems in full length. Hopefully it makes sense. If it doesn't, please watch the video once more or a couple of times if needed. And then let me know if you still have any questions. It's the exact same process. So at the beginning of confidence interval and hypothesis testing, I told you that is the same process that we are going to go over again and again for proportion, mean, and standard deviation. We're going to go over the same thing for proportion, mean, and standard deviation. And that was about a month ago or so. Okay. And I have gone through the entire process of confidence interval and hypothesis testing for you guys. And if you have followed along, you have learned a lot. And these are probably the most useful things, confidence interval and hypothesis testing, in addition to probability stuff and basic definitions that you have learned. You have learned a lot about statistics. By the way, if you have been keeping up from the beginning of the semester until now, you have gained a lot of information. So hopefully you are comfortable and you're okay with hypothesis testing. And this was the last topic for hypothesis testing, for standard deviation hypothesis testing or variance hypothesis testing. That concludes our month-long journey of confidence interval and hypothesis testing. probably the most useful thing in the class, or one of the most, along with probability. Okay, any question, anybody, before I move on to the next topic? All right, if no questions, we're going to talk about correlation. What is correlation? Correlation is the association or some relation between two variables. Okay? Correlation is the association between two variables. Okay? For example, if it's cloudy, you might carry an umbrella. Okay? Makes sense. It's cloudy, you might carry an umbrella because it might rain. Or if it's too hot, you might dress lightly. Or if it's too hot, you might drink a lot or have ice cream, stuff like that. So there are a couple of things here. Temperature and your behavior in one case. If the temperature is high, you tend to consume more drinks, or more cold drinks to be precise. Okay, or more, not even cold drinks, maybe even water. Okay, so there is a correlation between high temperature and drinking or taking fluids, or there's a correlation between cloudy weather and carrying an umbrella, or there is a correlation between cold weather and carrying or wearing heavier clothing. All these are correlated. But remember, these things like amount of liquid or fluid you consume and the temperature, they may be correlated, but don't think that the temperature causes you to drink more. You could afford not to drink even if the temperature is high. There could be other factors that's causing you to drink more. It's not the temperature directly in and of itself causing you to drink. It might be the case that because of high temperature, you release more body fluids. Okay, you sweat. Okay, you release more body fluids. So to keep up the balance, maybe your body needs more water or more fluid. That's why you consume more fluids. It's not the temperature itself that's causing it directly. So sometimes there are situations or there are variables that are correlated to each other. But remember, it does not mean that one causes the other. Correlation does not necessarily imply causation. That means, high temperature doesn't cause you to drink. There might be a correlation, but there might be other things. One good example would be this, which would be more clearer. I think I talk about it somewhere. Let's say during the winter time, you get the flu or the cold. That doesn't mean that the low temperature causes you to get flu or cold. It's not true. What is rather true is that during the cold season, when the temperature is low, the presence of certain bacteria in the environment is more common. Okay, and that is the bacteria that's causing you to have cold or flu or whatever it may be. So even though there is a correlation between cold temperature and having more frequent cold or flu, that doesn't mean that cold temperature in and of itself causes the flu. So keep that in mind. It could, but it doesn't necessarily mean that. Okay, correlation, there is correlation between two variables that could be measured, which we measure by linear correlation coefficient. In this case, we are going to be measuring linear correlation between two variables. So we measure it using linear correlation coefficient. This is the formula. Now, main thing to keep in mind, correlation does not mean causation. Another good example, during the springtime, okay, people tend to have allergy. So one might conclude that there is a correlation between springtime temperature and allergy. But actually, springtime doesn't cause you to have allergy. What causes allergy is the pollen in the air. During the springtime, there is more pollen in the air, and that causes you to have allergy. So I'm giving you these examples so that you can understand that there could be correlation between variables, but it does not mean that one causes the other. How do you measure correlation? Okay, well, let me give you a couple more examples. Let's say your city has a sales tax of 8%. So if you spend $100, you pay $8 tax. If you spend $200, you pay $16 tax. And if you spend $300, you'll pay $24 tax. So it's proportional. Okay, you cannot say, oh, I'm not going to pay $8 tax because just because I spent $100. I don't feel like paying that. You cannot say that. You cannot say I'm going to pay $5 instead of $8. No, it's strict. Okay, you have to follow. So there is a correlation between sales tax and the amount you spend. Oh, sorry, not this one. And the amount you spend. Okay, sales tax and the amount you spend. Correlation. That correlation is very strong and precise to the point, and that has a positive correlation, and that correlation is 1. That means there's the highest correlation value you could have. It is called perfect linear correlation. That means 1 for 1. Okay, there is a perfect linear correlation for the sales tax. You have to pay the exact amount. On the other hand, think of another scenario. When you go to a restaurant, at the restaurant, you are expected to pay 15%. You are expected to pay 15% tip. But do people pay 15% exactly? The answer is obviously no. Sometimes people pay less. Sometimes they pay more, or sometimes they pay exactly, or sometimes they pay nothing. Okay, they pay more or less or exactly 15% or pay nothing. There is no hard and fast rule, even though it is recommended that you pay 15%. It is recommended that you pay 15%. Now, there is a positive correlation between the amount you spend at a restaurant and the tips you pay, but this is not as strict as the sales tax. It is not as strict as the sales tax. So there is a positive correlation, but it's not as strong as 1. It's less than 1. Okay, less than 1. Now, we normally use bivariate data, which is basically XY pair. When you have paired data, it is also known as bivariate data. Easy way to visualize these data points is through the scatter plot. You basically plot the data points. Now, how do you measure the linear correlation coefficient? It's also known as Pearson linear correlation coefficient. It's denoted by R. And the person who invented it is, his name is Pearson. Okay, and it is measured by this. You will not be using this formula, by the way, to calculate the Pearson linear correlation coefficient, but rather, I'm just showing it to you. Okay, you'll be using calculator to find the R value. Now, if you look at this and this, you notice that these are standardized or normalized values. These are technically, if you're dealing with normal variables, I mean bell-shaped curve, then these are z-scores, okay? X minus x bar divided by the standard deviation of the sample, y minus y bar divided by the standard deviation of the samples of y. So these are normalized or standardized values, okay? So that's what you use, and you sum it over all possible values of x and then divide it by n minus 1. That means sample size minus 1. And this is how you calculate linear correlation coefficient. You don't have to use this formula. You just need to know that this is the formula that is being used to calculate linear correlation coefficient R, or Pearson linear correlation coefficient R. Okay. Now let's move on to the next thing. Some properties of linear correlation coefficient. What are the properties? Linear correlation coefficient, or Pearson linear correlation coefficient, falls between -1 and +1. That means the smallest value you could have is -1. Greatest value you could have is +1. Okay. Smallest value you could have is -1, and greatest value you could have is +1. And R is equal to 0 means no linear correlation. Okay. There might be other correlation, but no linear correlation. R less than 0 means it's negative correlation. Negative correlation. R greater than 0 means it is positive correlation. Okay, so one property of the Pearson linear correlation is that it's between -1 and +1. 0 means no correlation, no linear correlation. Okay, 0 means no linear correlation. There might be non-linear correlation, but no linear correlation. And R less than 0 means negative correlation, R greater than 0 means positive correlation. Number 2, R is equal to -1 means perfect negative correlation. And R is equal to +1 means perfect positive correlation. R is equal to 0 means no linear correlation between the variables. Okay, which I talked about actually right here too. R is equal to 0 indicates the absence of linear correlation, but there might be non-linear correlation between the variables that will not be discovered by R. Okay, R will not find out any non-linear correlation. Then there are a couple of rules of thumb. One is, if R is greater than 0.8, the highest value it could have is 1, right? If R is greater than 0.8, it is considered strong positive correlation. On the other hand, if R is less than 0.8, I mean -0.8, R is less than -0.8, then it is considered strong negative correlation. Think of negative correlation. One good example is gas price and number of miles driven. Okay, if the gas price goes up, what happens to the number of miles you drive? Goes down. So it is negative correlation. It is negative correlation. On the other hand, if the gas price goes down, the number of miles you drive goes up. So these two variables are negatively correlated. That means increase in one causes the decrease in the other. Increase in one causes the decrease in the other, or vice versa. Decrease in one causes the increase in the other variable. So that's what it is. Now, if you cautions, or at least one caution, when you are trying to find linear or Pearson linear correlation coefficient, make sure that you get rid of the extreme data points, because if you have extreme data points, then your linear correlation coefficient could be significantly affected. Okay? If you have extreme data points or outlier, okay, if you have, let's say you're finding correlation between number of transactions and the price of home, okay, you're trying to find out the number of transactions that happens and the price of home. So if you have one home, average home price, or the median rather, home price somewhere is let's say $500,000, but there is one home, $10 million. Okay, if you include that $10 million data point in the calculation, then you will be running into problem, because the $10 million is gonna change or have significant impact on the correlation. So you want to exclude data points, extreme data points like that, before you calculate your correlation coefficient or linear correlation coefficient. And just to do a visual observation of the data points, or use some software to find out if there are data points that are like more than 3 standard deviations away or something like that. Those are kind of really extreme points. So you may want to exclude those. The last property is that the Pearson linear correlation coefficient is not affected by scaling. What it means, let's say you want to find the correlation between age and height when people are growing up. You want to find the correlation between age and height. Let's say A is for age and H is for height. If you change the age from years to seconds, or height from inches to, feet to inches, that's not gonna make a difference. Or if you change the age from years to weeks and height from feet to, let's say, meters, that's not gonna have any effect. Because the reason it's not is, go back here, because of this, because it's all cannot a standardized form, okay? It's all standardized, kind of like z-score, so it really doesn't matter. So the point is that linear correlation coefficient is not affected by the change in units, okay? If you change the units, it's not going to have any effect. It's not gonna change anything. The correlation is still gonna be the same. So to summarize, we went over 5 different properties of Pearson linear correlation coefficient. It is between -1 and +1. Then -1 means perfect negative correlation, +1 means perfect positive correlation, R means no linear correlation. However, there might be non-linear correlation. Then rule of thumb, R is greater than 0.8, meaning strong positive correlation, R less than -0.8 is strong negative correlation. Linear correlation coefficient may be significantly affected by the presence of outliers or extreme data points, okay, in the bivariate data. Bivariate means it's a fancy name for XY pairs, okay? So it's recommended that you clean the data before you find the R. And then the last property, R is not affected by the units, okay? Linear correlation coefficient is not going to be affected by changing the units, so long you're consistent, okay? If you have all your units in feet for height, you can have it in feet. All units in meter for height, you can have it, okay? But don't mix units, like your height, half of your height is in feet and half of your height is in meters, then it won't work, of course, right? But you can change the entire unit and it should be fine. That kind of concludes linear correlation coefficient definition. Any question, anybody on this? Remember, linear correlation does not mean causation. There is correlation between two variables does not mean one variable causes the other. Easy way to remember is the flu and the cold season. Lower temperature does not cause you to have flu, but rather some bacteria that happens to be present during the cold weather that causes the flu and the cold. Okay. Similarly, for springtime does not cause you to have allergy, but rather the pollen from the trees that are more frequent or more present during the springtime that causes you to have allergy. So correlation existing between two variables does not mean one variable causes the other. Okay. Next is hypothesis testing involving correlation. We'll do a couple of problems on that, hypothesis testing involving correlation. But I think I'll stop here for the day. I will go ahead and work on these problems, hypothesis testing using correlation in the next class, which is going to be Monday. And then we are going to move on to linear regression. All right. We are going to move on to linear regression. And our semester is coming to an end, by the way. We have, after this month, we have a couple of weeks of class. Okay. So there are about 4 classes before the end of the semester, and then we are perfectly on time with things. And I'll be covering the linear regression as well as correlation. And I might cover something, if time permits, involving hypothesis testing, okay? It will be multiple populations, hypothesis testing for multiple populations, which I will probably cover briefly, okay? Hypothesis testing involving 2 or more populations. And again, we are going to do the PMS thing, all right? Proportion, mean, and standard deviation. So that depends on how much time we've got, but at least I'll try to cover one if time permits. All right, that's all for today, folks. Thank you so very much. You guys have a wonderful weekend and enjoy the rest of your week.